8.5 billion light-years away, so distant that the light reaching us left before our solar system even existed. The James Webb Space Telescope has spotted something extraordinary, a jellyfish galaxy, trailing long tentacle-like streams of gas and newborn stars behind it as it moves through space. Beautiful, bizarre, and scientifically extraordinary. Hey Space Family, welcome back to D3, Discover Deep Dreams, your educational gateway to the cosmos and beyond. I'm your co-captain, and today we are talking about one of the most visually stunning and scientifically fascinating discoveries from the James Webb Space Telescope. A jellyfish galaxy, the most distant one ever observed, spotted 8.5 billion light-years from Earth. And what it's revealing about how galaxies live, change, and die is rewriting what we thought we knew about galaxy evolution. Let's dive in. First, what exactly is a jellyfish galaxy? A jellyfish galaxy is a type of galaxy that has developed long trailing streamers of gas, dust, and stars extending from its main body, resembling the tentacles of a jellyfish drifting through water. These tentacles can stretch for tens of thousands of light years. Enormous structures of material being stripped away from the galaxy as it moves through space. They're visually striking. Images of nearby jellyfish galaxies show spectacular trailing structures, sometimes glowing with the blue light of newly forming stars, extending behind the galaxy like a cosmic wake. But jellyfish galaxies aren't just beautiful. They're scientifically important, because those tentacles tell a story about what's happening to the galaxy. And that story involves one of the most dramatic processes in the universe. Jellyfish galaxies are created by a process called ram pressure stripping. Here's how it works. Galaxies don't exist in empty space. Between galaxies within galaxy clusters, there is a diffuse hot gas called the intracluster medium. This gas is incredibly sparse, far thinner than the best vacuum we can create on Earth. But it's there, filling the space between galaxies within a cluster. When a galaxy moves through this intracluster medium, as galaxies do, orbiting within their clusters at hundreds of kilometers per second, the gas and dust within the galaxy experience a kind of headwind. Imagine holding your hand out of a car window at high speed. The pressure of the air rushing past pushes your hand backward. The same thing happens to the gas and dust in a galaxy moving through the intracluster medium. The ram pressure, the pressure of the galaxy's motion through the surrounding gas, strips material from the galaxy, pushing it backward into those long trailing tentacles. The stripped material doesn't just drift away passively, it gets compressed and disturbed by the stripping process. And that compression triggers star formation. New stars are born within the tentacles themselves, lighting them up with the blue glow of young, hot, massive stars. This is why jellyfish galaxies are so visually spectacular. They're not just trailing debris, they're actively forming stars in streamers that extend far beyond the main body of the galaxy. Until recently, jellyfish galaxies had only been observed in the relatively nearby universe, within a few billion light-years of Earth. At those distances, we could study them in detail, but we were only seeing the universe as it is relatively recently. The James Webb Space Telescope has changed that completely. By detecting this jellyfish galaxy 8.5 billion light-years away, Webb is showing us a jellyfish galaxy as it existed 8.5 billion years ago, when the universe was less than half its current age. This is the most distant jellyfish galaxy ever observed, and it tells us that ram pressure stripping was happening in the early universe too, not just in the relatively recent cosmic past. This matters enormously for our understanding of galaxy evolution. One of the central questions in astronomy is how galaxies change over cosmic time, how the vibrant star-forming spiral galaxies of the early universe gradually transform into the quieter, redder elliptical galaxies we see more commonly today. Ram pressure stripping is one of the key mechanisms driving that transformation. When a galaxy loses its gas to stripping, it loses the raw material for forming new stars. Eventually, the star formation slows, stops, and the galaxy ages, becoming what astronomers call a quenched galaxy. Finding Ram pressure stripping happening at this cosmic distance, this early in the universe's history, tells us that this quenching process was already at work billions of years earlier than we previously had evidence for. Let's talk about why James Webb could find this when no telescope before it could. The Jellyfish galaxy in question is extraordinarily distant. At 8.5 billion light-years, it appears incredibly small and faint in the sky. The tentacle structures, which are the defining feature of a jellyfish galaxy, are even fainter than the main galaxy body. Detecting them at this distance requires a combination of sensitivity, resolution, and infrared capability that simply didn't exist before Webb. Webb's primary mirror, 6.5 meters in diameter, collects dramatically more light than any previous space telescope. Its infrared sensitivity allows it to detect the glow of distant galaxies whose light has been redshifted, stretched toward longer wavelengths by the expansion of the universe, in ways that optical telescopes simply cannot. And Webb's resolution, its ability to distinguish fine detail at extreme distances, is what allowed astronomers to actually see the tentacle structures in this distant galaxy, rather than just seeing a blurry smudge. This discovery is a perfect example of what Webb was built to do: peer back into the early universe and reveal cosmic processes that were previously invisible to us. Every discovery like this one is a demonstration of Webb's extraordinary capability. One of the most remarkable aspects of this jellyfish galaxy discovery is what Webb detected within the tentacles themselves. The streamer structures trailing behind this distant galaxy aren't just gas being swept away. Webb detected the signatures of star formation occurring within the tentacles, new stars being born in the stripped material, as it gets compressed and disturbed by the Ram pressure stripping process. This is consistent with what we see in nearby jellyfish galaxies. But seeing it at this cosmic distance, at this early epoch in the universe's history, is extraordinary. It tells us that the physics of star formation in stripped material is universal. The same processes happening in nearby galaxies billions of years ago were happening in the same way in galaxies 8.5 billion light-years away. The tentacles of this distant jellyfish galaxy are a stellar nursery. New stars being born even as the galaxy loses the material that will eventually quench its star formation entirely. It's beautiful and tragic at the same time. A galaxy giving birth to stars in the very process of being slowly starved of the material it needs to keep forming them. This discovery opens new doors for galaxy evolution research. With Webb now demonstrating that jellyfish galaxies can be detected at these extreme distances, astronomers will be searching for more, building a sample of distant jellyfish galaxies that can reveal how Ram pressure stripping has operated across cosmic time. Combined with the Roman Space Telescope's wide-field surveys, which will map enormous swathes of the sky in search of interesting targets, the coming decade promises an explosion in our understanding of how galaxies evolve, transform, and eventually age into quiescence. The Jellyfish galaxy is one piece of a puzzle that astronomers have been assembling for decades, and with Webb, the pieces are coming together faster than ever. 8.5 billion light-years away, in a universe less than half its current age, a galaxy trailing tentacles of gas and newborn stars through the ancient cosmos, beautiful, dramatic, and slowly losing the material that will one day silence its star formation forever. The James Webb Space Telescope found it, and in doing so, it pushed our understanding of galaxy evolution billions of years further back in cosmic history. That's what Webb was built for. That's what science is for, reaching further, seeing deeper, understanding more. And that is exactly why we keep looking up. If you like space exploration, don't forget to like, subscribe, and ring that notification bell so you never miss a single D3 episode. Keep looking up.